追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science, that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而恒谦，雾河多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台， 探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，硕玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。 世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。 邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，雾河多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席， 秉持科学、公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞明明。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学、公正的原则，严格遵照评审流程和标准。 这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向， 为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域，这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学、公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔雁栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而恒千，物合多容，星云璀璨，黑洞明明。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years. And they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，雾河多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而恒千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔雁栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域，这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。
Now it's on. So I was problem with this microphone being on is you cannot ask a question. Everybody knowing what I'm asking. The only thing is now there's background graph vertices where you do that. This is one thing you can use. I have a million components. It's not like one culture.
So here's what you have to record. You have to record whatever your goal is. Okay. So algebra, whatever that is going to be something where every, if you consider it as a stratified space, like every point has a neighborhood as a stratified space, which belongs to the subject. Okay, then that's what this will be.
Okay, I think that makes sense. I think I understand. Excellent.
Okay, are you ready? Okay. All right, so before I introduce the speaker, let me make an announcement. So as some of you might know, there was a talk here at 1 p.m. by Coach Bikar. Since he got sick, it got canceled, but it's rescheduled at this very room, 8:30 a.m. on Friday morning. So, okay, so with that said, it's a great pleasure to have one of our esteemed colleagues and friends, Professor Mohammed Abu Zaid. He's a Frontiers of Science Award winner, and he's going to talk about homological mirror symmetry without any corrections, and he's from Stanford University, if I didn't mention. Please go ahead.
Thank you very much. It's a pleasure to be here at this event, and it's an honor to receive this award. It's a little bit unusual for me to be giving this lecture because the category that this is in is like commutative algebra and algebraic geometry, and I am not a commutative. I'm not algebraist, and I'm not an algebraic geometer. I'm some kind of geometer. The reason behind that, I think, is somehow that I work in mirror symmetry, and I work on the other side. Mirror symmetry is about the relationship between two subjects, algebraic geometry and symplectic topology, and I work on the other side. And the way you should think about at least one thing that we do in mirror symmetry is produce algebraic varieties, even though the talk will explain how it's kind of delicate whether we have algebraic varieties or some more like analytic spaces, out of some purely topological data. Okay? And the title of this lecture is something, homological mirror symmetry without corrections. And this basically, what you should imagine is what this means is the simplest family of examples where some complicated feature called corrections do not arise. And I'm not going to say more about that because that's basically what we're doing, except towards the very end, where I will explain some strategy for extending the results, which this paper was about, to a more general situation. Okay, and the other thing I'm going to do is that the slides that I prepared are, well, kind of dense and set up in some very general context. But what I will do, some of you maybe can read this, is I will try to illustrate everything in the simplest, lowest dimensional situation where there's something non-trivial to say. And the lowest dimensional situation is the setting of Riemann surfaces maybe you want to think of them instead as algebraic curves. So as the slides say, mirror symmetry is some phenomenon discovered by string theorists. It's about Calabi-Yau varieties, which are projective algebraic varieties with trivial canonical bundles. So what does that mean? In the simplest setting, it means basically the tangent space is trivial. And for Riemann surfaces, as people know, there's a classification. From a topologist point of view, there is a two-sphere, and then a torus, and then higher genus objects. And this one has Euler characteristic 2, this one has Euler characteristic 0, and these have negative Euler characteristic. And this trivial canonical bundle situation basically distinguishes this case. Okay? So the initial part of the subject for the first 10 or 15 years was about Calabi-Yau varieties, which means about this. And then there was an extension to what are called Fano varieties. That would be about P1. We're not going to talk about that. But now these days one can do things that are more general. But this lecture is about doing something relatively sophisticated, very complicated about mirror symmetry, but doing it in the simplest case. So the physicists, when they discovered this phenomenon, they discovered some kind of duality. Okay? They discovered, you look at Calabi-Yau threefolds, things so from the real point of view, so they have complex dimension 3, and they discovered some kind of involution. So look at this one, and you can find a matching dual one. And the relationship between them is kind of mysterious. As I wrote here, the relationship is about on the one side, some kind of periods. So you kind of integrate volumes of certain objects with respect to natural choices of the choice of holomorphic volume form, because that's the triviality of this object. This thing, if you write it as a quotient of C by a lattice, okay, what we'll do is you can take dz as a volume form on C will descend to a volume form on this object. So that's the that's a holomorphic volume form we're talking about. That's one side of the picture. It's about integrating holomorphic differential forms on cycles. And the other side is more mysterious. It also has roots in kind of older mathematics. It's some kind of refined version of enumerative geometry. Enumerative geometry is counting 27 lines on a cubic. This is kind of maybe the most famous non-trivial example that goes beyond Euclidean geometry, which is just 2 lines through any point. Okay, so it's counting curves on higher dimensional spaces. And what they discovered is that if you take these counts of curves on Calabi-Yau varieties and you put them in kind of generating functions, what you get is something that corresponds to these period integrals on the mirror side. And it's a mysterious subject, and we still don't know. There are many things we don't know about it. The one thing that I want to say, again, I'm doing like anti-hype. Okay? The one thing that is most mysterious is that it turns out that these two pieces of data, okay, we have this x, and this x check, and on both sides you have this kind of, period integrals, and here say enumerative. Okay? And on the other side you also have this enumerative thing, and this kind of period stuff. Okay? And this matches up with this, and this matches up with this, for the same pair. And this is something that mathematicians still don't really understand. And what we've done for about 30 years, and this talk is some continuation of it, is say we're going to just ignore. Okay? We're going to ignore one of these two correspondences and look at only one of them, like say this one. Okay? And when you ignore this one, when you ignore the other one, really, what happens is that this structure, this count of holomorphic curves, you can now think of it as not having to do with algebraic varieties. Okay? This is now something that you can think about just symplectic manifold. And this thing here, well, it's still about an algebraic variety, but it's not about some kind of being projective or anything like that. It's just about the variety itself. So this is the abstract variety. You don't use the projective structure. And what is maybe slightly surprising is that once we did this, once mathematicians decided to ignore the perfectness of the duality in a certain sense and think about only one side, then we discovered new mirror phenomena that were not understood by the physicists. Which means, in particular, we discover some situations where there are some varieties that are not projective, okay, that happen to have symplectic mirrors, okay, and vice versa in a slightly more complicated way. So that's, this kind of forgetting, as very often happens in mathematics. Once you forget some of the structure, you discover new phenomena that you didn't have access to before. Okay, so the last thing on the slide that I want to mention is that very early on, there was some extension due to Kontsevich, or some really kind of vision due to Kontsevich, that in addition to these extremely concrete enumerative questions you can ask, there is some deeper phenomenon, which is some kind of categorical equivalence. Okay, so this is, it really was some kind of vision at the time, because on the symplectic side, the structure didn't even exist. And this is really what this lecture is about. In the title, there is the word homological. And here the word homological is about some categorical structure. So on this side, it's not a very complicated category. It's not an unfamiliar categorical structure. It is basically the study of coherent sheaves. Okay? And if you do commutative algebra instead of algebraic geometry, it's a study of modules over rings. Okay? Now, something to really derived category, so you're looking at maybe complexes of modules, but ultimately that's what this is. And on this side, if you're just studying symplectic topology, then this is something that really at the time had barely been, the existence had barely been suggested by Fukaya. I think he's chairing another session. And it is about the structure of certain submanifolds in symplectic manifolds, okay? Lagrangians. Okay. So this is a lot of stuff, and what I want to do now is say something about elliptic curves. Okay. Before moving on to the next slide, I just want to say a few words about what this means. So the study of elliptic curves occurs in many, many parts of mathematics. So one thing that is probably very familiar to people is that you can think of there's a picture like this. Okay, it lives in the upper half plane. I'm not sure I'm going to get it right. And this, in some sense, is recording the moduli space of elliptic curves, the space of all as algebraic varieties, the space of elliptic curves over the complex numbers up to isomorphism. So this picture arises by exactly thinking about lattices in C up to possible transformations, holomorphic transformations, linear transformations. And so you can think of so you have a lattice, you have two vectors, you take the first vector, you put it in this direction here, and then the second vector you can put somewhere, okay? And so this gives you some other vector tau. And then there are more transformations you can do, like shears, and then by the shears you can bring tau back to here, but also you can swap the role of tau and 1, and that's how you end up with only some upper part, whatever. Let me not worry about this too much. So there's this parameter tau that lives in some domain, think of it as living in some domain in C, that parametrizes the choice of elliptic curve up to isomorphism. On the other side, there's this word symplectic, which I assume people are not familiar with. But what it means simply is it is a smooth manifold equipped with an area, with some notion of an area form. Okay, so in higher dimensions, what does it mean to have area? Well, it's a 2 form, satisfying some nice properties, it's closed. But in dimension 2, it literally means an area form. Okay, and if you have any familiarity with differential topology is extremely flexible. Okay, so all Riemann surfaces which have the same genus, okay, and are equipped with an area form that has the same total area are actually equivalent by a diffeomorphism that takes the area form on one side to the other. So in this case, there's only one parameter. So this is the algebraic side. There's this parameter tau, and on the symplectic side, there is a parameter which may be called A, and it lives in 0 infinite. Okay, and then you're like, how am I going to match up this tau with this A? That doesn't make sense because this tau has like two real dimensions, and this A is one real dimension. Okay? And of course you can't. That's the point. So what happens is, what you can do is you can match up tau with some kind of complexification of A. Okay? But we're going to if you just stick for a moment with something very basic, remember what I'm going to say is we're going to try to ignore most of the structure. And before I started the first slide, I said the way we're going to think about this is we're going to take symplectic manifolds and produce some kind of algebraic varieties out of them. So it may be difficult to produce all of them. In this case, all I should do is I should focus, giving an A, which tau should I get? And it turns out that the answer is very explicit, and this was known to Kontsevich in probably one of the first computations he did, is that you get the A's that correspond to this. Okay? So another way to say this is that this A gives you exactly those elliptic curves which are in some sense rectangular. Okay? That's not all of them. In fact, it's far from all of them. But that is the correspondence. And my hope is by the end of the talk, you have, actually by about a third of the talk, you have some idea about how, once starting with some symplectic manifold, with this symplectic manifold, maybe some additional structure, which I'll talk about in a second, you can somehow produce this object. Okay? And it looks the same, but here you want to produce this object, with its complex structure. Whereas here you just have a smooth thing with an area form. Okay, so I will move on to the next part. So, physicists came up with this conjecture. Mathematicians, can check it. It's some specific claims. You can check those claims. But at some point, mathematicians become dissatisfied with just checking claims. We would like to understand why things are true. Okay, like some kind of higher conceptual phenomenon. And this first proposal was, in fact, in some sense, still the only real proposal, was due to Strominger, Young, and Zaslow in about 95. And they said, well, what we should have is some additional structure. This X and this X check, okay, they should maybe project to some common base. Okay? And this common base should be the base of a fibration. So in their case, they said there's this very specific word, special Lagrangian fibration. The word here, special, is some geometric, some very rigid geometric notion that is required in order to be able to make sense of this double duality that's floating around. Okay? But for me, again, since I'm going to split it in half, the only thing that really matters is this Lagrangian structure. And a Lagrangian structure is just the vanishing of this form, being half-dimensional and having the property that this symplectic form vanishes. But in this case of tori, Lagrangian is just a curve. Lagrangian in symplectic manifold X just corresponds to a curve, one-dimensional curve in a Riemann surface. So what is a Lagrangian torus fibration on a 2 torus? Well, that's really quite simple. The thing is two-dimensional. You can project it to the circle. Okay? And there are some features here that are quite concrete. In particular, you can somehow normalize things so that the fiber has size 1. Some kind of canonical thing you can always do. And then, in the base, you now have the length of the base. This corresponds to the total area. Okay, A. So now, this correspondence that I told you about, which we'll get to in a second, is, I told you that the total area should determine some kind of modular parameter for some elliptic curve, and it should be this one. But one way to do it is to have this intermediate step where I tell you, like, I'm going to just draw a circle of length A, and using the circle of length A, I can produce a symplectic manifold, and I can also produce an algebraic variety. So how are you supposed to produce this? The proposal of Strominger and Zaslow was exactly that you should dualize the fibers. Okay? So dualize the fibers, and this explicit case means you take the fiber, you write it as R mod lattice, you take the dual lattice. Okay? There is a more abstract point of view, which is that if the fiber is L, which is I'm gonna just say abstractly isomorphic to an N torus, okay? Then the dual fiber, I should think of it as the first cohomology of L with coefficients in R mod Z. This is some vector space. But most important thing that I want to say about this is that I can think of this as parametrizing local systems of rank 1. Okay. Right now I'm working with kind of, maybe this would be IR. Okay. Where what's happening here is this is identified with S1, and S1 is the same thing as U1, maybe unitary, sorry. Unitary. Local systems of rank 1. Okay. And now abstractly, because the first Betti number of an N torus is N, this is again an N torus. But correct way to think about it is this is the dual N torus. And this can be made very explicit. So that's the proposal, you put it together. And then there is one piece of relatively elementary mathematics that I don't want to go through right now, which says that if you have such a situation, and if on this side, maybe this side, I'm going to switch my two sides. If on one side you have a symplectic form, you do this dualization, on the other side, magically you get a complex structure, and the complex structure is integrable. Okay? So that's really their proposal. You can just, the dualization procedure really swaps symplectic structure. The property, in fact, of being closed is essential here for a complex structure, and the property of being integrable is essential. So we produce locally some kind of complex manifolds just out of symplectic topology in this projection. Great, so now I'm going to do the same thing. I'm going to say a familiar thing to do in these lectures, just state the main theorem. So what does the main theorem say? So it says, so I'm just going to go through it. It has some words. I know there's some technical assumptions. So X is a closed symplectic manifold. And now I tried to state it carefully. If you have Lagrangian torus vibration over some base, okay? So that's this base here that we're talking about. And I'm sorry, let me correct this. So this one goes here. Good, corrected. Okay, of some base. And then there's some assumption. Pi2 of this base is 0. Okay? There is no known example of something closed symplectic manifold with a vibration over some base where this condition is not satisfied. So you should really think of it as just some technical condition that doesn't affect any example that we know about. And then equipped with a section, I should have said Lagrangian section. So sometimes you can write vibrations over sometimes projection maps don't have sections. Okay, if you have a section, then this structure, okay, this geometric structure or maybe topological structure of a manifold with a projection map to some base, and this, so the fibers are tori, Lagrangian tori, it determines some mirror space. Let's call it X check. I call it the SY is a mirror space. And moreover, some faithful embedding, okay, of two categories. Of what? Of this object called f of x. This is the Fukaya category of x. This is this mysterious thing that Fukaya discovered in 93, 94, and that is the subject of this mirror symmetry. So it's an object which is more familiar, which is some derived category of coherence. Okay? So there's the main things that are not satisfactory about this theorem is this technical assumption about pi2 of q. Okay? Or let me say it differently. The things that are obviously not satisfactory are this pi2 of q assumption. This condition of being a fully faithful embedding, what it means is everything that you could try to compute on the symplectic side, you can transfer into a question on the algebraic side, and that question and whatever answer you get on the algebraic side is what you were looking for. Okay? So what it means technically is that the morphism spaces here are isomorphic to the morphism spaces that you get on the other side. This is not as good a condition. You want to prove something stronger. You want to prove some kind of backwards construction. You want to show that every object you could see on this side, every module over the ring that you would be considering on this side actually comes from some symplectic objects. And this, I will explain some strategy for getting this. In reality, in examples that we actually care about, this is not too hard to do. But it would be nice to have a very general proof. Okay. Okay. And now, as I say at the end, we unfortunately, the real gap is that this condition of having Lagrangian torus fibration, of course it works in this case and works for abelian varieties for some kind of tori, but there's much wider class of examples to which it doesn't apply. In particular, the initial examples that the string theorists cared about, which is kind of quintic threefold, or even the K3 surface. You can't use this machine, but it's supposed to be a first step. Okay, any questions before I move on? No? Good. So now I have to say some technical stuff. So the technical stuff, unfortunately, is about what it means to look at this derived category of coherencies. So this X check, I said it's a mirror space. I tried to be careful. It is not in general a variety. So in fact, there are some famous examples. So Kodaira has some classification of surfaces, and in the classification of surfaces, he discusses complex surfaces, and then it's well understood which complex surfaces, analytic surfaces, have an algebraic structures and which do not. And there are some of them that are basically quotients of Euclidean, some kind of quotient of Euclidean space by some group action, but not by an abelian group. So these are called Kodaira surfaces, some of the Kodaira surfaces, and those have mirrors in this sense. And so clearly, this notion of mirror symmetry is more general than what the string theorists hoped for, and so we have to go outside the algebraic category. Okay, and we have to go also. So we have to work with analytic geometry, and unfortunately, the most technical part of the subject is the fact that we don't work in analytic geometry in the usual sense that is taught in undergraduate courses. We have to do something called rigid analytic geometry. We have to replace the notion of Archimedean norm by some kind of t-adic norm. So this is the ring that symplectic topologists always work with. So we call it the Novikov ring. It has Novikov field, let's say. It has some origins in the study of, so Novikov studied the maps from manifolds from topological spaces to the circle and wanted to do some analog of Morse theory, and he introduced this ring. So this definition requires a choice of a base ring. So that's what I call the base ring K. Okay? And then you look at power series with finitely many negative exponents, but in some variable t. But now the thing that is unusual is that the exponents are allowed to be real numbers. So what is the size of an element of this ring? The size of an element of this ring has nothing to do with the AIs. What it has to do with is the smallest lambda I that shows up. Technically, that's 1 over the norm, but you extract it from this information. Okay, and using this notion of size, you can do many. This is kind of classical. Maybe Tate is the first person to develop a very elaborate, kind of essentially complete theory of doing analytic geometry over such rings. And that is the nature of the space X check. Okay? And how do you produce it? You produce it essentially by what I was telling you over here. Okay? So this point, if you are not, I'm not an algebraic geometer. So if you're not an algebraic geometer, you try to think of a space as a bunch of points with some extra structure that tells me how they're glued together. So the points of this space are given as follows. I choose a fiber, okay? And over there I use the term maybe Q for little q. Like choose a point in the base. That determines this fiber here, okay? And then on this fiber, what I'm supposed to, the space of points that correspond in XCheck that correspond to this thing here are all possible local systems. So local systems, as I was saying over there, means if I go around, I have some monodromy, I have an element of the circle. And each such thing, there's some package called Floer theory, which I will not talk about, which produces some groups. Some groups associated to what? So groups associated to any other Lagrangian. So if I draw this L is some Lagrangian instead of symplectic manifold. In this setting, it's just a curve. I can use something called Floer theory to produce a group associated to L and this fiber XQ. And these groups, or really modules over some ring, something like that, as they vary from point to point, form a sheaf. That is the content of the first part where I said there is a functor from this to this. Okay? The functor from this to this means I can do this construction. Okay. So proving that this forms a sheaf actually takes quite a bit of work. This is what's done in this paragraph. And I don't want to talk too much about it before I run out of time, but I want to say one thing, which is usually when people think about mirror symmetry, we think about the complex numbers. But in this setting, actually, you can choose an arbitrary ring. You can work over Z, you can work over the sphere spectrum if you know what that is. But that raises this question that I put at the end, which I just don't understand very well, which is we expect some situations where we can prove that the outcome of our construction, this analytic space that we produce, is in fact algebraic. It comes from an algebraic variety, is controlled by some polynomial equations, if you want to say it like that. But it's not clear to me whether it makes sense to ask this question independently of the ring. Like, can you have something which is algebraic over F3 but not over F7? I don't know. And it's not that plausible to me that there'll be examples out of this specific construction, but in the generalization that I'll be talking about later, this is very likely to happen, and we already know some situations where we can prove mirror symmetry, but only for small primes. Okay, and that's very likely. I mean, this is one possible explanation for what's going on. That somehow there's a difference between algebraicity and analyticity, depending on the characteristic. Okay, so this is kind of very.
Can I ask?
Yes.
So in higher dimension, so this realization that you dualize the lattice and then you take the quotient, and then naturally, because it's dimension 1 on the elliptic curve, you get this H1 tells you the whole core to the mirror. But in higher dimensions, obviously, you cannot use this argument.
No, so this works just as well as long as the total space. I'll say a few words. As long as the total space actually has a Lagrangian torus fibrations with no singularities, the same procedure works.
Okay.
But if you have singularities, you need another approach. And this is what I will say in the second part.
Okay.
But okay. So now I want to talk about, this is kind of well, what is the strategy? How do we do this? Okay. Well, things like varieties are defined by local constructions. We know what affine things are, and then you glue them together. Okay? That's basically how it works. So even though we're in some analytic setting, the analytic setting also has the same thing. You know what a complex manifold, we know what a open subset of Cn is, and you know what a biholomorphism is, and then you can glue things together. Okay? So what you want to do is take this point of view as your starting point, and then use it to define this mirror function. Okay? So what you should do first is understand what happens in a small neighborhood of one Lagrangian. And that's a small neighborhood of one Lagrangian. In symplectic topology, we understand very well. There is something called a tubular neighborhood theorem, kind of typical in differential topology. And the tubular neighborhood looks like the cotangent bundle of an n-torus. So first, we should understand mirror symmetry for the cotangent bundle of an n-torus, which means in this dimension, that means understanding mirror symmetry for this object. So this is T star S1, which is r times s1 with some specific, with the area form that you see on the blackboard. There's basically only one area form. And mirror symmetry for this was understood before we understood that it had to do with mirror symmetry. So what I'm trying to say here is simply that Floer-theoretic invariants of objects like of this nature, cotangent bundles, have relatively explicit descriptions that is related to the topology of the base. Okay? So I'm now using some other kind of area of mathematics, but I'm basically saying we know how to understand Floer theory here, and we know how to relate it to the group ring of the fundamental group of the base. Okay, how does that arise? Well, it'll take me quite a while to explain, but the basic idea is that there is some Lagrangian that lives over here, okay? And that is somehow dual to an inclusion at 0 inside the cotangent direction of the symplectic manifold of the manifold that you care about, which is a circle. Okay? And now, by doing some Floer theoretic computation with this object here, what you extract is a group, and that group happens to be, again, for reasons having essentially nothing to do with mirror symmetry. It happens to be, well, the ground ring, which I'll just call K here, with two variables Z and Z inverse, and Z corresponds to moving in this direction, and Z inverse corresponds to moving in this direction. Okay? There's some very explicit way in which this picture that I'm drawing with a line and then rotating it around this way and rotating it around this way generates a ring, which is exactly Laurent polynomials in one variable. And now Laurent polynomials and variables, of course, the ring of functions on C star. Spec K ZZ inverse is C star. But people could do algebraic geometry of GM or something like that. I'm just going to do that. C. Oh, this is C. I should make that C, so I don't have to think about it. Okay, and that's in some sense, the first, and well, again, other than the point, which is not much to say, the first non-trivial mirror statement, even though, of course, the string theorists would be like, why are you caring about this? It's certainly not something that people in the 80s thought about. And this is some duality between, again, there's a mirror duality between these two objects. This object as an object as a part of algebraic geometry, and this object as a symplectic thing. Okay. Now we look at this picture. Okay. This is a symplectic picture. And in this picture, this elliptic curve, this two torus with finite area, okay, has in it a circle. Okay? And inside the circle, there is a small annulus. And this small annulus is, I want to think about it as a small region here. Now it's clear, I cannot fit this entire R times S1 inside this two torus because I will run out of area. Okay? This has finite area, that has infinite area, it doesn't work. And now, what the correct thing to do involves completion. Okay? So it's similar, there's exactly analogous procedure in this case. Okay? If I told you that, okay, C star, great. Now let's look inside C star as an analytic domain. Let's look at an annulus. Okay? Let's say this is 1 and this is like some number. I won't call it A really, but it's really e to the A. Okay, so 1 radius. Things between norm of Z is between 1 and 1. Okay, and now I asked, what is the ring of functions on this thing? Well, as an algebra, it's not an algebraic variety, but it's an analytic thing. Whatever it is, you can, in first course on complex analysis, you would learn that this is a ring of functions. The ring of functions on this is just a completion of Laurent polynomials. So in both algebraic geometry, we realize analytic geometry, and in symplectic topology, going from the big domain to a small domain corresponds to completing the ring. Okay? This is completely familiar on the algebraic side. On the symplectic side, it's a relatively new point of view. At the time that I wrote the paper, it was probably not written anywhere explicitly. By now, again, in the third part of the talk, I will explain that now there's some kind of big machine to handle it, to think how to think about it. And once you have this, you're in some sense done, because all you have to do then is take your symplectic manifold and break it up into some pieces. Okay, it's going to be horrible, but okay, you break it up into some pieces, and Each of them, okay, just by cover, you cover it by pieces that look like these small annuli. For each of them, you know what the mirror is, and so therefore you can patch together what you want. And if you go through this procedure, you will see exactly this correspondence between A and 1 over tau that I asserted at the beginning. But that turns out to be the easy part. Okay, that's like, okay, I constructed the mirror. I understood some procedure for taking a symplectic manifold and producing an algebraic object out of it, as long as I have this data of the projection. Okay? That turns out to be the easy part. Slightly more complicated is this next part where you take Floer homology with some, if you take a Lagrangian and you take this Floer homology group, okay, this is already a more technical thing to do, but this is not so bad. So both of those things were written in some ICM address 2014, but really all I did there is I put in some well understood things that experts already knew, and I just put them on ink. Okay? The real hard part is to prove that this procedure, this is the last part, part 3, that this procedure respects morphisms. Okay? And it's kind of the reason it's very hard is because in symplectic topology things are not supposed to be local. Okay? I didn't describe anything. I didn't describe to you how to define Floer homology because that would be another lecture. But the fundamental problem is that in general things are not local. So you need to develop some actual tools to say that in this case, for this situation, it turns out to be. Okay? And given that we're working in some very large generality, it's not even clear what tools to use. And it turns out that there's a paragraph here that says something like, what you're really supposed to do, or what I really did, is think on the other side, use this cover by affinoid domains, by small domains, and use it to resolve the diagonal. Now, normally, when people hear the word resolve the diagonal, they're working with some kind of finite kind of objects. The push forwards of these things are not finite, they're huge. But in some sense, it was still possible to make sense out of it and then prove this equivalence. So this is mostly all I want to say about this before moving on. Any questions? No. Yes? Yes, I will say some things towards the end. I have no idea how much time I've left. There's no clock in this room. Okay, good. So I'm running late. That's what you're saying. So singular Lagrangians. So in practice, we have singularities. Okay. So once you encounter singular Lagrangians, there's two things. First, you can say, I'm going to study the simplest case of singular Lagrangians. And it turns out that the simplest cases of singular Lagrangians are what's called immersed Lagrangians. And all I want to do is draw a picture here that's so that we have some idea that we're on the same page. Actually, there's a picture on the next slide anyway. But
so maybe you're gonna say it, one quick thing. When you do these patch gluings,
yes.
So this functoriality seems like obviously gluing needs to follow, but then you cannot glue unless you do it homologically.
Everything is...
higher dimensions again.
Yes. The hardest part, not the hardest part, one of the things that makes things complicated is that everything is working at the level of the derived category.
Okay.
So we have to glue things with chain complexes, and there are higher coherences, and there were some words about it, but I decided to skip that part. Okay, so I'll actually skip this slide because it's easier. Okay, this picture. This is the picture we have in mind. Okay, in 2 dimensions, you can start with a smooth fiber, which is a 2 torus. Okay, and I gave you some story saying this smooth fiber, you should think of its mirror as being like the dual torus, and so it's again a rank 2 kind of object. But then this thing degenerates into an immersed P1. Okay, and that's the domain of this immersion. And this thing has no interesting local systems. Okay, so where is the structure coming from? And what symplectic topologists, here there's a name, Akaho, and then Akaho and Joyce understood, is that what you should do is that there should be a contribution to this kind of space that we're trying to construct coming out of the self-intersection. Okay? What are you supposed to do? You are supposed to do some counts that involve these counts, self-intersections in a non-trivial way, and there's a picture illustrated here, which is something like this. If you encounter some polygon, and it goes through some self-immersion point called P1, P2, P3, P1, let's say P1, P2, P2, P1, P2, P3, great, okay? Imagine that each variable P, each intersection point P, is associated to each one of them is associated a variable called Z. So there's Z1, Z2, Z3. You count how many P1s you see, and then you see, oh, there's 2 of them. So I should get I get a term factor z1 squared, and I see 2 p2s, so I get d2 squared, d2 cubed, maybe 3 p2s, and then a z3. So this is some monomial that is contributed by this disk. Okay, so this is nice, but it turns out that if you look at Calabi-Yau threefolds, which is the thing we're interested in, let me step one step back. If you look at surfaces, like the K3 surface, this is the kind of singularity you will encounter generically. But if you look at Calabi-Yau threefolds, you will get something much worse. Okay? And for a long time, this was some kind of stopping point. We're like, how are we going to handle this phenomenon? But it turns out that even though the singularities of these fibrations are pretty bad, there's always plenty of immersed Lagrangians, which means Lagrangians that are not quite embedded, but whenever they meet, they just meet along double points. This is not the technical definition, but that's how you should think about it. They meet along double points, and double points Floer theory can handle. Okay? So you can just say, are there enough of them? Can I find plenty? And the answer is yes. So we don't know the answer to be yes in complete generality, but we know the answer to be yes for some class of singularities that were studied by Gross and Siebert. They studied toroidal degenerations of Calabi-Yaus, and then they identified somehow the essential class of singularities as the following. So you're working in dimension n plus m, okay? But there's this +1 here because I'm about to describe a hypersurface, okay? So inside Cm plus 1 and C star to the n, the variables are x, x1 through xm plus x0 through xm plus 1 through xm for the complex ones, and y1 through yn for the ones which have a puncture. You look at this hypersurface. Okay. So maybe, I assume people haven't seen this before. So one toy case of this is when there are no y variables, you get product xi equals 1. Well, this is just C star to the m. Okay? That's the case we've studied before. But as soon as you have something like this, let's do the first one. If you do instead x1, x2 equals 1 plus y, okay? This is very interesting space. So this is actually C2, these 2 variables, minus, so y is not allowed to be 0. So it's C2 minus 1, complement of 1. And this turns out to be a very interesting space. It's the only space other than tori which is self-mirror. Okay. So I will illustrate this in a second after stating the main theorem. So this is a follow-up. This result was proved a few years later. It was with Zach Sylvan. I think Gamage has an alternate approach using some micro-local method. Okay, and it says there's 2 variables, m and n. Okay, and mirror symmetry holds if you swap them. Okay, so if I look at the chi category of this object, if you look at Lagrangian submanifold inside this symplectic manifold defined by this equation, then I get the same thing as coherent sheaves on the variety where I swap n and m. And if you specialize the story here, you'll see that because of this +1 over there, what happens is this says that this is self-mirror. So how is this done? Again, I don't have that much time, but this is done basically by finding some interesting Lagrangians on one side. Ooh, I'm going too fast. Finding some interesting Lagrangians on one side and doing the same kind of strategy as suggested before. Studying its Floer theory very carefully, trying to understand, extracting from it the algebra, the equation for the mirror space. So this is not some kind of, you compute this on one side, you compute this on the other side, and you see they match up. It's really, you look at this side, you stare at it really hard, and you see the other side appear to you with all its structure. Okay? So there's some more discussion of examples. I think I already did them over here. What I want to say is that there's some very interesting question, but the extent to which this can be generalized. It's really hard to do Floer theory in some very general sense. It's very hard to compute Floer homology groups. But there's an approach of Pomerleano which probably can be extended to this to a more general mirror setting that Gross and Siebert have been working on for the last 5 years. They call this intrinsic mirror symmetry. We'll see if if this can be pushed further. But this case is already hard enough, and I'm happy. I mostly want to talk about this. Okay, so that addresses one of the questions, which is how do you deal with some more singular things? And the short answer is I can't do the general case, but there's much wider class for which we can now do at least local mirror symmetry results. Now, back to Artem's question, how do you do the gluing? Okay, and in this initial paper, the gluing was basically done by hand. The paper is extremely long and very technical. But these days, we have a new technique for doing it, and this is called Floer cohomology with support. So this is the last thing I will say. So this technique was introduced by Varul Ganesh in his thesis in 2018. And let me just go through. There's 3 ingredients. So the first ingredient is something kind of shocking if you have familiarity with symplectic topology. And it says something like this. So if you have some symplectic manifold X, and you take any compact subset, if I knew how to draw the Cantor set, I would draw the Cantor set, but okay, a compact subset. Then there is some way of assigning to every Lagrangian submanifold L, some kind of Floer group that depends on K. Okay? And we think of it as the Floer cohomology with support on K. Okay? Its definition I will not give, but its definition is related to using the characteristic function of K, really using the characteristic function of the complement of K. Okay? And then you use it in the construction, and most important thing to say about it is that it cannot be defined without using the t-adic topology that I mentioned in the beginning. Okay? This is not something, I said, oh, you can work over this ring, this base ring. This is not about the base ring. It's really about this analytic part of the kind of notion of norm that we have on the Novikov ring. Okay, so we have to define these groups. So he defined these groups. And as I say in this remark, the first thing to realize is that they depend on more than the intersection. And to have some idea for what I mean, let's do, if this K is like this, and if I look at this is K, and this is putatively what L is, okay? Then there are many possibilities. So one possibility is that you extend K like that. You extend L like that, okay? That's one possibility. Another possibility is maybe you extend L like that. Sorry, maybe I should use the color that's in my hand. Okay, so these are 2 possible ways of taking the intersection of K with L and extending it to the outside. And these give rise to different groups. Okay, it's a fundamentally important fact that this theory is not local. Okay? But there is some theorem, it's in progress. If you take a sufficiently small neighborhood of an SYZ fiber, okay, and there's some extra assumption on L that I didn't write here. So going back to the situation, it's you take one of these small annuli, and there's some condition on L which I omitted over there. And in this very special case, it turns out that this local group, this group would support, maybe this is something that algebraic geometers would be happy with our terminology, this group with support can be computed in terms of the intersection. Okay? So this we call a locality isomorphism. It is not true in general. Once you have something like this, it feels very close to what people in algebraic geometry expect. Okay? So what am I going to say next? What I'm going to say next is, if you have something like this, then you could just say, I have these categories, I have these actual charts, and I can try to glue them together the way that they're glued on the symplectic manifold, the way they're glued in algebraic geometry, but also on the symplectic side. So let's move on. So the next ingredient that you would need is some kind of functoriality. So this is supposed to illustrate for you, I said everything has to do with characteristic functions. If K is a subset of K prime, then the characteristic function of K of the complement is greater than or equal to the characteristic function of K prime, and this goes into the definition of the fact that you have this map. There is a map. It turns out then that everything is multiplicative between the Floer cohomology with support on K prime and the Floer cohomology with support on K. If you restrict support, it's completely reasonable. Well, maybe, yes, that's completely reasonable. Okay, so moreover, if you have a triple inclusion, this map is associative. So this is starting to look like a pre-sheaf. Okay, and the last thing to say, one thing to do to show that the pre-sheaf forms a sheaf is you have to prove some kind of exactness. So we're working in chain complexes. So I'm sorry, I have to do it like this. So this was proved. This version of this was proved in Varul Ganesh's thesis. So he showed that if you are now in a special, even more special situation, which is that we have a projection to some base. I use the word integrable system over there just to indicate that it's more general than this SYZ situation. You have projection to some base. You have 2 pieces of the base called Q1 and Q2. Okay, so this is Q1 and this is Q2. And what you want to do is you want to compute the thing associated to the intersection, the union knowing the thing associated to the intersection? And the answer is there is a long exact sequence. Okay? So this is the correct analog in the setting of chain complexes, or the derived setting of the usual, the usual sheaf axiom. Okay? So we have something like a sheaf. In fact, I think we have like a Grothendieck topology determined by the projection, but anyway, it doesn't matter. Okay, great. We're almost done. So this tells us that there is now a new strategy for doing local to global mirror symmetry. This is not implemented, being written at the moment. And it would extend the earlier work that I did almost 10 years ago, not quite, maybe 8 years ago. So first, we need to, I told you about some groups associated to Lagrangians and subsets, but actually we need to define Fukaya categories. Okay? Then I told you about the restriction maps. Well, we need to make those into functors. And finally, given some integrable system, given some projection to some base, we need to prove an analog of this gluing statement. So it's probably going to be a homotypical black square of categories, whatever that means. Okay, but most importantly, this is what it looks like on the other side. This, when you say coherent sheaves on algebraic varieties given by some formula, that formula is exactly, you locally define what the rings of modules are coherent modules, then you check that restriction maps satisfy what you want, then you define the thing to be the thing that satisfies the gluing. Like you just, this is by definition how it's done. But in symplectic topology, it's not by definition. You have to you produce it intrinsically, and then you have to check this property holds. Okay? And finally, if you have this, and you've checked that locally the pieces match up, then you can, and how so interesting, then you can say, I have proved mirror symmetry. Okay? Now the last thing I will say, actually let's do something else. The first is that there is some decategorified version of this, which is already in the literature. So I wrote it with Roman and Volugnesh in 21. By decategorified, that means you go from categories to vector spaces by taking Hochschild homology. Actually, Hochschild cohomology, and we do it as frame D2 algebras, but it's another story. Okay? And then the last thing to say is that if you are the kind of person for whom mirror symmetry means things like computing Picard-Fuchs equations, this is going to be very disappointing, okay? Because the answer that we produce here is very abstract, and it's really hard to pin down which mirror variety we get you, okay? So I think, this, again, great, I can be happy that some project, once this is done, I can be done with this project, but we will not be done. Mathematically, we will not really be done, because then the goal will then be to relate what comes out of this to other approaches and understand how this relates to the Hodge theoretic picture. Thank you very much.
All right, thank you. Questions?
Can you say why, say on the algebraic side, you can expect that this neighborhood of this Lagrangian vibration is so special? Is there some hint from the algebraic side?
Well, so what I can say is something like this. So in Tate's old approach to rigid analytic spaces, okay, he defined the notion of an affinoid ring and defined rigid analytic spaces as things that are glued together, things by glued together affinoid ring. And these neighborhoods of these fibers, that is basically what they give you. Okay, they don't give you, so in fact, the smooth fiber, they actually give you something called Laurent domains, which are somehow the first thing that Tate talks about. The other ones are probably not, I don't know how to produce a general affinoid ring out of symplectic topology, but they just give you some generalizations, some classes of examples for which we can understand, for which mirror symmetry holds. We don't expect mirror symmetry holds for everything. Anyway, that's the answer that I can give.
Okay, thank you.
More questions?
So when you want to glue things, you need to glue charts, right? The charts are defined by affine rings, so you need the compatibility of ring structures, right? So you mentioned some exact sequence, so I think...
Yeah, so this exact sequence is in, sorry, go the other way.
Yeah.
This sequence. Yeah.
So these preserve ring structures?
Yeah, so these, yes. So this is a ring map. It is the map that is associated to restricting from the union to each component. And this is a ring map. It is the thing that is associated to restricting from each component to the double intersections. And now these things on the other side, you don't want to think about them. I just stated it like this because this is the easy thing to state on cohomology. The thing that you state at the chain level is that something is the cone of something else. Okay? So, and that the map that appears in that map is a ring map. And which then transfers to this pullback square property. Anyway, I'll tell you a little bit more later.
Okay.
May I ask about the setup? The difference between setup of Tate and Berkovich.
So now you can see that I'm not an expert. I know enough to know that this is a question that I don't want to answer. So let me just say one thing. So I believe in these situations it does. So my understanding is the difference is how many points you have. Okay, Berkovich has many more points. Okay, for these things it doesn't really matter because we know what the rings of functions are. I can transfer this computation in the Tate setting to the Berkovich setting, and I don't think it would give me anything new. Okay, I think what's interesting, I do want to say this, is that it's the Novikov ring is the thing that appears naturally for us in symplectic topology, but it might not be big enough for some applications where we want to take some comparisons of something, where they make some comparisons with something algebraic. Maybe that's the only thing. Something from the other side. Like, for example, in characteristic 0, the Novikov ring is over an algebraically closed field, it's algebraically closed. But in characteristic P, that is not true. Okay? So there are certainly going to be, there has to be some input that we're going to have to take from analytic, rigid analytic geometry, more sophisticated than Tate's paper. But I think right now we have not needed it. So I haven't.
Thank you.
Yeah, so for the singular fibers, can you also allow the singularities like some torus degenerate into lower dimensional torus?
So the philosophy, which I went through very quickly, is every example that I have explicitly thought about has the following property. Somebody hands me a very singular Lagrangian, and I find near it some immersed Lagrangian which captures all its Floer theory.
So okay? like torus fibrations, like you
pick some. Yeah, let me just say one thing. So one thing you encounter, for example, is you can encounter the situation where it is a 2 torus and it pinches to a point. Right. This is the first thing you said. You have a torus and it collapses to a. This is the first thing that you would say. So Floer theory has no idea how to deal with this. I mean, maybe somebody, maybe not in this room, somebody who's really good at analysis, can kind of figure out how to do Lagrangian, how to do pseudo-holomorphic disk with boundary conditions on this stuff, but nobody knows how to do it. Okay. But here's what you can do. You can take this thing and you can take 2 copies of it, and you can connect them like that. Okay, whatever that picture means to you. What it is some 2 torus times an interval, but it's not embedded. It's actually immersed in such a way that it meets itself along a 2 torus here. Okay. Well, this is something I know how to do Floer theory for. And if you look at this paper with Sylvan that I cited, it is basically about doing that. You study the Floer theory for this guy, and what happens is that there's some holomorphic disk that sits right here, and that captures the fact that there was a singularity. So that's the strategy that I know how to implement.
Okay, thanks.
You replace the singularity of the submanifold, or whatever, the subfright, whatever, by some immersed thing that is nearby. Okay, and this is now just philosophy. The immersed thing nearby bounds some disks, and those disks change the Floer theory of this immersed thing in such a way that it appears to reflect the singularity that you had. Okay, but this is just because you cannot define the other one. Because you cannot Yeah. So at this point, we don't. If a holomorphic disk escapes to that point, I don't know what to do. And I've not known what to do for as long as I've been a mathematician. So the only thing I know how to do is to do that. And it works surprisingly well in this class of examples.
Okay, let me ask you a quick question myself. So in this SYZ fibration example, right? Let's say on the algebraic side, I have skyscraper sheaf point. I know that this is a special Lagrangian here. So then algebraic geometry says over there I'm doing intersections, and this should be compatible with intersections there. So over there, for example, I can take a structure sheaf, extension between a structure ship and a skyscraper, which is a finite thing.
Yeah.
So what is it mirror of? Oh, that's a section or multi-section.
So,
am I right?
Yeah.
So is this how you guys recover?
Yeah. So the nicest thing to say is actually there is a geometric procedure. I mean, I'm not sure on the symplectic side, which is as follows: if you took two Lagrangians, this one and this one, okay. So you're saying you want to do intersection, and I think you're thinking of intersection homologically,
exactly.
X groups.
Yes.
Okay. So symplectically, we can take this thing and we can produce out of it a new Lagrangian by a surgery procedure. Okay? And this surgery procedure, in the simplest situations, matches up exactly with this geometric construction. And this is, for example, how if I did the two torus, I could explain to you how you produce all the line bundles. All the line bundles are obtained by twisting the trivial line bundle by points. Okay, and you could just do that. I mean, actually, they have not all of them because the Picard group is non-trivial, but then ultimately you can get them as sum ends. There's also kind of taking components. So that you can, everything is describable in terms of pictures and is completely precise in dimension 1. In higher dimensions, it's more delicate.
Okay, so one more question.
Yeah.
We have algebraic varieties which have full exceptional collection given by line bundles. So do you have something like an exceptional collection?
Well, first of all, I assume they're not Calabi-Yau.
And
yeah. So that would be some other talk and some other setting where we're talking about phonos. This is actually, I think, a very interesting question. In the simplest setting, we can indeed see some exceptional collections in symplectic topology exactly arising as Lagrangians which meet in a certain way, as predicted.
Mm-hmm.
But there are some papers. I believe recently there's been some paper about like two different exceptional collections on the same variety which are not related by an autoequivalence. I do not know how to see that symplectically. I think that's an interesting question, but it's slightly tangential to the talk.
Okay. Thank you so much. Let's thank the speaker. I think next talk is in 15 minutes.
Yeah.
穹苍广而横千，雾河多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。 世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量。理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔雁栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程三大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流，追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。 邱成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the forefront of all these subjects that will be beneficial to human beings. This will be a very successful event that will be influential to the whole subject of fundamental science that will be beneficial to all human beings.
从古至今，从未知到已知，科学家以有限的人力探问无穷的宇宙。基础科学不断拓宽人类认知的边界与疆域，这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命，一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会
Okay, are you ready?
I think so, yeah.
Okay. Welcome again. It's great pleasure to have our colleague and friend for many years, Professor Davish Malik from MIT, who is going to talk about one of his Frontiers of Science Awards out of 2 that he got received this year. And he's going to talk about P equal to W conjecture for GLM. Please.
Great. Thank you for the invitation. Is this microphone working for you guys? Is it too loud? No? All right. If it is, let me know. Okay, so thanks for the introduction. Thanks for the opportunity to speak here. So what I would like to talk about today is what's called the P equals W conjecture, which is a conjecture involving about the subject of non-abelian Hodge theory for curves. Everything I'll be talking about that's kind of my own work is joined with my collaborator, Junliang Shen, who wanted to be here but couldn't make it. So let me begin by just talking about a little bit about non-abelian Hodge theory for curves before talking about what this conjecture says. So first, let me just fix for this talk. C is going to be a curve, usually of genus greater than 2, greater than or equal to 2. And I'm going to go ahead and fix a rank and a degree, which will be coprime. And so the non-abelian Hodge correspondence, at least the version I'm going to use, involves 2 different moduli spaces associated to this curve. So the first moduli space is what's called the moduli space of Higgs bundles, which is some kind of algebraic moduli space of some kind of algebraic gadgets associated to the curve. It'll be parameterizing what are called Higgs bundles, which consists of 2 pieces of data. The first is going to be a vector bundle E of rank R and degree D. And the second is this theta is what's called a Higgs field. It's going to be an endomorphism of E twisted by the canonical bundle of the curve. Okay? So it's 2 pieces. A Higgs bundle consists of 2 pieces of data, E and theta. And to get a reasonable moduli space, I'm going to impose a stability condition. So I'm going to look at what are called stable Higgs bundles. And I won't write down the definition of stability, but if you're familiar with stable bundles for a curve, it's the same definition involving the slope, the ratio of the degree to the rank, except I'm only going to consider subbundles that are preserved by this twisted endomorphism. Okay. So the way you should think about this Higgs field, so okay, vector bundles maybe we're okay with. The way to think about this Higgs field is that, okay, so theta is an element of Hom from E to E tensor K. And then by Serre duality, you can think of this Hom as dual to x1 of E comma E. And this x1 is the tangent space at E to the moduli space of vector bundles on a curve. So you should think of this as a cotangent vector. At this point in the moduli space of bundles. And more generally, you should think of the moduli space of Higgs bundles, if I ignore stability, as something like the kind of total space, the cotangent bundle of the moduli space of bundles. So for instance, if I restrict myself to stable bundles, the moduli space of Higgs bundles contains the cotangent bundle of the moduli stable bundles. And this is like an open, dense subvariety. But it's bigger because you can have Higgs bundles where the underlying bundle is not stable. So this is a strictly larger. But this is still a useful perspective. For instance, there's a natural symplectic form on this cotangent bundle because it's a cotangent bundle. And that extends to a symplectic form on this whole moduli space. So for instance, this moduli space of Higgs bundles is algebraic symplectic. And in fact, it's what's called a hyperkähler. Yeah. Right, so this is moduli space of stable bundles. So yeah, if I did the full stack of bundles, then that would be bigger than the moduli space of stable bundles, yeah. So if I ignore stability, then the stack of all Higgs bundles with this erased is literally just the cotangent stack to the moduli stack of all bundles. Okay. So this is the first moduli space. It's the moduli space of Higgs bundles on the curve. And again, it's parameterizing something, some algebraic or holomorphic data associated to C. The second moduli space is what's going to be called the character variety, or sometimes the twisted character variety associated to C. And it's something that doesn't depend on the algebraic structure of C at all. So what this is going to parameterize is I'm going to fix some points on my curve. And I'm going to just look for representations of pi 1. So this is going to be mapped from the fundamental group of C minus P. So I'm going to puncture my curve at this point P. And just look for homomorphisms to GL R of C. With the property that if I look at the loop around my puncture, that gets sent to a scalar matrix given by a certain primitive rth root of unity, depending on D. Okay. And I want to look at these homomorphisms up to conjugation. Okay, so this is, again, usually called the twisted character variety. Twist because I'm imposing this condition on the puncture. And so the only thing I'll say about this space right now is that this is smooth. Both of these spaces are smooth because of this co-prime condition I put here with stability. But this variety is an affine variety. So this is actually an affine variety. And it's not such a mysterious object because this pi 1 is very explicit. So if you really, at least before I take the quotient, you can really just think of this as a bunch of matrices a bunch of invertible complex matrices with the property that the product of their commutators is this scalar matrix. But I still have to then mod out by the GLR action. Okay. So these are my two moduli spaces, this algebraic one and this more topological one. And so then the statement, which is some case of non-abelian Hodge theory. Okay, I won't write the. So this is non-abelian Hodge theory. And this is the subject was developed basically in the 80s by many people, but the kind of main names I'll write down are kind of Corlett, Donaldson, Hitchin, and Simpson. Said that these two moduli spaces, the moduli space of Higgs bundles and this character variety, which is are naturally in bijection with each other, and in fact, there's a C infinity diffeomorphism between them. So this is really kind of, this is a theorem of, really some kind of analytic content to it. The way this theorem is proven is that there's some, third space of, what are vector bundles with some kind of special metric on them, like a harmonic metric, and then you specialize to each of these two different spaces in some way and show that each of those specialization maps is in fact a diffeomorphism. But let's see what this correspondence looks like just in the case of R equals 1, where you don't kind of need a huge machine to understand it. So the left-hand side, this moduli space of Higgs bundles. So remember, a Higgs bundle, which I've erased the definition for, is a vector bundle and then this kind of twisted one form. If I'm in rank 1, the vector bundle is just a line bundle. So I'm going to look at, say, maybe I'll call it just degree D line bundles. And that, endomorphism valued one form just is a one form. Okay. That's the left-hand side of this correspondence. The right-hand side of this correspondence, well, again, it's just going to be, you know, 1 by 1 invertible matrices, and the product of the commutators needs to be 1. So that's just C star to the 2G. And so then you can just kind of eyeball what this kind of diffeomorphism is going to look like. This is just a complex torus, and this is just a complex vector space. So this is going to be S1 to the 2G cross C to the G. And if I rearrange this, I can kind of regroup things. So this is kind of, you know, S1 cross R to the 2G. And then this S1 cross R you can identify with C star. Okay, so that's how you can think about this diffeomorphism in this example. And already in this case, you see something kind of important, which is that, you know, whatever this diffeomorphism is, it is completely brutal when it comes to the algebraic or even just the complex analytic structure. And that's something that's true in general. So this, I'll put a star here. So star is, you know, badly disrespects the complex analytic structure. And one way of seeing that in general is that, well, the right-hand side, as I said before, is always an affine variety. In particular, it has no positive dimensional compact subvarieties. Of the left-hand side, on the other hand, admits a proper surjective map to some lower dimensional affine space. So D here is just half the dimension. Which is called the Hitchin map. And one way of thinking about what this map is that this affine space is just spec of the ring of global functions. But you can also study it more explicitly if you want. Okay. But I'm not going to do that. But this Hitchin map is going to play a major role in this talk. But for now, let me just point out that in particular implies that these things can't be isomorphic as complex manifolds because I have all these fibers, which are, you know, half-dimensional proper subvarieties of the Higgs moduli space. And one way of thinking about what this map looks like is that it turns out that this, the fibers of this map are Lagrangian with respect to the symplectic form on the Higgs moduli space. So the generic fiber of this is going to be some kind of smooth abelian variety. But then as I kind of, you know, specialize my fiber, I'll pick up kind of complicated singularities. And the fiber over 0 is some kind of, you know, non-reduced, reducible mess. Okay. Are there any questions so far while I gather my notes? So just to summarize, what we have right now is two moduli spaces associated with my curve, this algebraic one and this topological one, and this kind of, you know, transcendental diffeomorphism between them. And so the vague question you can ask whenever you're in this situation is that if I have a kind of diffeomorphism between two algebraic varieties, you can ask, let me keep it on the board, which algebraic structures on one side have some meaning on the other side. So for instance, a question which I will not say anything about because I don't know anything about it, is you could ask which algebraic subvarieties on one side are still algebraic on the other side. And I actually don't know if there's even a good proposal for the answer to that question. So this P equals W conjecture is about a specific example of that question, where I'm going to take something kind of algebraically defined on the character variety and move it over and try to find some interpretation for it on the Higgs moduli space. Okay, let me say what this conjecture is about. So remember, I have this diffeomorphism between these two moduli spaces. And so in particular, if I look at just their singular cohomology, using this diffeomorphism from non-abelian Hodge theory, I can identify their singular cohomology. And now, using the fact that, for instance, the right-hand side is not just some topological space, but an algebraic variety, this cohomology carries some extra structure. And so the particular extra structure that I'm interested in is going to come from mixed Hodge theory. So if I look at the singular cohomology of this affine variety, in particular, well, okay, it has a mixed Hodge structure. But in particular, that means it carries an increasing filtration called the weight filtration. This is defined by Deline in the 70s. And this is an increasing filtration that starts in, well, if I'm doing cohomology in degree j, the weight filtration will start at weight j, and then increase until I stop at weight 2j. Now, in general, it's a little hard to define. The way you should think about this lowest piece is that these are the cohomology classes on this open variety that extend to some compactification, some smooth compactification. But in general, the other pieces are a little hard to get your hands on in general. However, in the specific case of the character variety, the weights, or at least their graded pieces, have another interpretation, which I want to explain. So in this case, a result of Hausel, Rodriguez, Villegas, and Nick Katz show the following, which is that they relate this weight filtration to counting points on the character variety. So I won't write this down, but the character variety, I gave you the equations for it, and they were defined over some ring of integers as long as I have that root of unity. And so if I count points on the character variety over a finite field, well, first of all, this is a polynomial function of Q. Let's call it f of Q. And what are the coefficients of this polynomial? Well, they exactly come for the dimensions of the graded pieces of the weight filtration. So more precisely, if I take Q to the dimension hold on a second. I have to switch from Q to Q inverse because I'm not doing compactly supported cohomology. This is equal to f of Q. So in other words, in this case, the dimensions of the graded pieces with respect to the weight filtration exactly tell me about just counting points on this character variety over finite fields. And so that's another interpretation of what this weight filtration is telling us. It's giving us some kind of arithmetic content about this character variety. Oh, the star is, I'm summing over, I'm ignoring the cohomological degree. So I'm taking an Euler characteristic with respect to that. So this is summing over star and J. Yeah, thank you. Okay. All right, so this is some structure now defined on the right-hand side of this equality, this weight filtration. And it's something that depends, the way this filtration is defined, it depends on the structure of this character variety as an algebraic variety. And so the question then, this kind of vague question, is what meaning does this have? What meaning does this weight filtration have? So this is defined with respect to the character variety. What does it mean on the other side? Okay, the way I've written it is actually a yes or no question. And this would not be a very interesting talk if the answer were no. So in fact, I'll say the answer to this question is yes. Let me tell you what it is. Well, first, maybe before I do that, let me tell you what it isn't. So you could ask, maybe the first guess would be that maybe it just corresponds to the weight filtration on the other side. Okay. So first, this is not the weight filtration on the Higgs moduli space. Because it turns out the weight filtration on the Higgs moduli space is what's called pure. It only lives in that lowest piece. So the weight filtration on the Higgs moduli space is not so interesting. The weight filtration on the character variety is very complicated. So instead, the answer, which was proposed by De Cataldo, Housel, and Migliorini around 2010, is to study instead what's called the perverse filtration. Which has to do with the topology of that Hitchin map that I defined before. So recall, if I have this Higgs moduli space, it has a structure of a Lagrangian fibration over some affine space of half dimension. And the topology of this fibration you can use to define a filtration on the cohomology of the Higgs moduli space. And I'll give two definitions of it. So first of all, what I want to say is this pi defines a filtration on the cohomology of the Higgs moduli space. So I'll give two ways of thinking about this. First, let me give the original definition, which is not so illuminating, and then I'll give a more topological way of thinking about it. So the original definition is what I'm going to do is I'm going to take the constant sheaf, so with respect to the analytic topology, and I'm going to push it forward to my base. So this is going to happen inside of the constructible derived category of sheaves on affine space. And so using what's called the decomposition theorem, this derived push forward splits as a direct sum of shifted perverse sheaves. So I won't define perverse sheaves, but the way I want you to think about this is that if this map were just a smooth map in addition to being projective, then each of these perverse sheaves would actually just be a shifted local system corresponding to the cohomology of degree A of the fibers. So over the smooth locus, this PA is basically the local system cohomology. But then as the fibers become more and more singular, whatever this object is becomes more and more complicated. And then how do we define a filtration using this? Well, I'm just going to define a filtration by taking the first, however many summands of this direct sum and taking their contribution to the cohomology. So the kth piece of the perverse filtration is just going to be the cohomology of just instead of taking the whole summation, I'm just going to take the first k plus 1 pieces. If this were a smooth map, this would be normally what we would call the Leray filtration. But because it's not a smooth map, I have to kind of throw the word perverse on top of it. It's because PA is not, this is not actually a local system. It's shifted by D. So then I just want to shift it back. No, the idea is that local systems are not perverse sheaves. You have to shift them by D. So I'm just kind of compensating for that. Okay. All right, so this is the definition. It's very hard to think about, at least for me. So let me give you another way of thinking about it, which is due to Di Cataldo and Miglerini. From 2008, which says the following. So again, I take my Hitchin map from the Higgs moduli space to affine space. And then inside of this affine space, I'm going to take kind of a descending flag of affine subspaces. So let's say this is codimension 1, so D minus 1, D minus 2, and so on. Okay. And these are always kind of generically chosen. And then I can take their preimage upstairs. So this is contained in pi inverse of lambda d minus 1, pi inverse of lambda d minus 2, and so on. And so another way of thinking about this perverse filtration is as the kernel of various restriction maps to these subvarieties. Okay, so this is equal to the kernel of the restriction map, the cohomology of M Higgs, to the cohomology of one of these preimages. So what is this saying? So, for instance, if this family were just a trivial family, then all of these restriction maps would be kind of an isomorphism, except for the very last one, which is just the 0 map. And so in that case, this perverse filtration is just 0 until you reach k equal to star, in which case it's everything. But once you start picking up some singular fibers, then these kernels become more and more interesting, and you get a more interesting filtration. And so I want you to think about this kind of verse filtration as measuring the as some measure of the complexity of the singularities of this map. Okay. So do I have time? I have 15 minutes? No. 25 minutes. Okay. Oh, great. Okay. So let's just do it before I state the conjecture, which I think you can guess what it is. Let me just do an example, a couple of examples of what this perverse filtration looks like using this definition, which is a lot easier to kind of work with. Okay, so the first example is one I just kind of said out loud, which is this case of r equals 1. So in that case, as you might remember, the Higgs moduli space is just degree D line bundles cross affine space. And the Hitchin map is just projection onto the second factor. So it is one of these, basically a trivial fibration in that case. And so just by tracing through these definitions, you see that P, the kth piece of the perverse filtration is equal to 0 if k is less than j, and is equal to everything if k is equal to j. Let's do a more interesting example. So I'm going to take, this comes from a certain rank 2 family, but I'll just tell you what the geometry looks like. I'm going to take an elliptic curve cross A1 and mod out by the action of plus or minus 1 on both factors. This gives me some double point singularities, which I can then resolve. And then it has a projection to A1, which is just mapping onto the second factor. So A1 mod plus or minus 1 is just A1. And so this is what the Hitchin map is going to be in this case. And concretely, what this looks like is that this is going to be an elliptic surface over A1, where all the fibers are kind of, you know, the same, except for the central fiber, which looks like this. So what does the cohomology of this look like? So the cohomology of this space, because, you know, there's just one singular fiber, I can just deformation retract everything onto that central fiber. So in H0, I get something one-dimensional. H1, I get something zero-dimensional. And H2, I get something five-dimensional. Okay. But now if I study what happens to the perverse filtration, using that definition that I just erased, what you see is that, okay, this class has perversity 0. But these five, hard to see using just the Kunith formula and just using what we know about C star, that this will kind of only jump when the weight is equal to twice the cohomological degree. And again, that just follows from a calculation for C star itself, where in degree 1, that class has weight 2. This example is more interesting. I didn't really tell you what this is as a moduli space of Higgs bundles. It turns out it's related to a, not a P1 with some kind of orbifold structure. But I'll just tell you what the character variety looks like. Which it looks like I take a cubic surface inside of P3. And then I take the complement of, you know, a kind of triangle of lines. So this is the character variety side. And okay, well, I won't do the calculation, but you can at least do the point count to see what the dimensions of the weight pieces are. And so if I do the point count, I get 1 plus 4q plus q squared. Yeah, this is really like rank 2 with like maybe parabolic or something. Yeah. And so, well, okay, this would have been more convincing if I hadn't erased the perverse calculation, but this 141 is exactly what I saw on the other side. Okay, so this matches. At least numerically it matches with this kind of q to the 4q. So let me say now what we know and some of the background. Actually, before I do that, let me just say why this conjecture is maybe interesting. So first of all, where did it come from? Why did they propose this conjecture? Well, the idea was that Hausel and his Rodriguez-Villegas, who I mentioned before, had done a lot of calculations of these kinds of point counts on the character variety side, and noticed that they were always getting this kind of palindromic symmetry. On the other hand, that kind of symmetry is automatic from the point of view of this perverse filtration on the Higgs side. And so basically, this conjecture was proposed as a way of explaining that. And so more generally, one reason why this conjecture is interesting is that it kind of has interesting implications in each direction. So why is it interesting? It has kind of non-trivial constraints in each direction. So for instance, this is what I just said, this perverse filtration, because of how it's defined using perverse sheaves, always has this kind of, palindromic kind of hard Lefschetz structure. And so it implies that if I look at the graded, associated graded with respect to the weight filtration of the cohomology of the character variety, satisfies a version of kind of the hard Lefschetz theorem. It's kind of a surprising version of it because this is now some non-compact variety, so it's not going to be anything like the usual version of hard Lefschetz. And this is why it's usually called the curious hard Lefschetz. And it turns out later on, this kind of property was proven directly. So this was proven directly by Mellet, Anton, in maybe 2019, something like that. In the other direction, the weight filtration, because of how kind of naturally it's defined, is compatible with cup product. So in the other direction, for instance, implies that the perverse filtration and that's something that's very non-obvious. It's not always true. So this is something that is usually not true. If I give you some random, proper fibration, the perverse filtration usually will not behave well with respect to multiplication. So it's something special about this Hitchin map. Maybe let me mention, since Yukinobu is here, another interesting consequence of the P equals W conjecture, which is how I got interested in it, is that this implies a conjecture we made from 2016 regarding curve counting on Calabi-Yau threefolds in the special case when the Calabi-Yau threefold is the total space of the canonical bundle plus the structure sheaf. I won't go into this. Hopefully, if you were at his talk, then maybe you heard about this. But the point is that what this conjecture said was that if I look at your favorite curve counting theory on X, Gromov-Witten theory, DT theory, whatever, it should be equivalent to some kind of Euler characteristics of some perverse sheaves on some other moduli space associated to X. In this special case, using the P equals W conjecture, you can read that off from some appropriate point counting. So this ends up relating, let's say, the Gromov-Witten theory of X to some kind of point counts on one of these character varieties. And both of these have been worked out, a long time ago, so you can just check they match. Okay. So now let me say a little bit about what we know. The history. So when they proposed this conjecture, 2010, they didn't just propose it, they also proved it in a highly non-trivial case. They showed it when the rank is 2 and genus is arbitrary. That's a real kind of, it's an intricate argument, but it's kind of very convincing, I think. Then Mark, myself, and Junliang, many years later, showed it in kind of the other extreme example, which is all rank, but only genus 2. So kind of the other extreme. And then finally, now we have kind of 3 proofs of this conjecture in general. So myself and Junliang, Housel, Manetz, Mallet, and Schiffman. From 2022. And then there was another proof found by myself, Junliang, and Qizhang Yin the next year. Okay. And this is kind of the general case, all G, all rank. Sorry, how much time do I have left? 5 minutes? Okay, great. Let me just say what we don't know about this conjecture. So the original conjecture, I guess, has been proven. But there's a lot we don't understand. Well, first is at the very beginning of this talk, I kind of put myself in the coprime situation. But you could try to work in the non-coprime case. Now the moduli spaces are singular. And then you can try to kind of study things there, either using, for instance, intersection cohomology, or work with something like the homology of the stack. Okay, there are formulations in both settings, and they're kind of known to be equivalent to each other, but neither one is known. The second thing we don't really understand is the case of other groups. So I kind of focused everywhere on the case of GLN. But non-abelian Hodge theory is something you can talk about for arbitrary reductive groups. And this conjecture, the analogous conjecture can be formulated, but it's, I think, wide open. And for instance, we still don't know how to do it in the case of SLR. So still in type A. And then finally, and I think most kind of relevant, is the way I've kind of phrased this as conjecture about kind of, these moduli spaces that show up in non-abelian Hodge theory. But I think the feeling of everyone who's thought about it is that this is somehow just an artifact of how we kind of discovered this phenomenon. And that there should be kind of some much more general version of this correspondence that happens in kind of varieties that have nothing to do with, Higgs bundles on a curve or anything like that. And so, for instance, there's work of, let's say, Zili Zhang on cluster varieties, and so on. I think what we're missing right now is exactly what are the right adjectives you need to put in order for something like this to be true. Okay. So in just a few minutes I have left, let me just say a little bit about what kind of goes into these arguments. In particular, maybe I'll kind of focus on this first one because that's the one kind of I'm here for. And so what all of these proofs have in common is to really focus on the perverse filtration side, on the Higgs moduli space side, and try to understand some of these surprising properties about it. For instance, I said before that one kind of surprising implication of the conjecture is that it's compatible with cut product. And so basically one thing that has to go on is you try to have to kind of understand those properties directly. And I give two definitions of the perverse filtration. And those definitions have many redeeming qualities, but they're just not good for the kind of fine analyses you need to prove this conjecture. So all three of the arguments use some kind of extra symmetries in the problem to help control this perverse filtration better. So the idea is to use some kind of extra symmetries. So for instance, in this first proof, the idea is to exploit what's called a global Springer theory, which was developed by Ngo and Zhuai Yun, I don't know, a long time ago, let's say 2008. In this proof of Hausel, Mellet, Minette, and Schiffman, they use the structure of what's called a cohomological Hall algebra, which is some kind of, Hecke-type algebra, which they show acts more or less on the cohomology of these moduli spaces, and they use that to kind of find some extra symmetries. And then finally, this last proof is less representation theoretic, and the idea is to instead use some kind of, partially defined Fourier-Mukai transform. So some symmetry of the derived category, and use that to help understand the perverse filtration. Okay, let me stop here. Thank you.
Questions?
Okay, thanks. I would like to ask, do you have any comments on the P equal to W conjecture on wild character varieties?
No, no, that's another open. Interesting, but I don't have any. I mean, a lot of the steps that we use, some of them will apply in that setting, but a lot of them break down. So I don't think a lot of the arguments we have don't apply in that setting right now, I think.
But is there any evidence that this will still hold?
Oh yeah, I think that's a situation where I think people believe it quite strongly. There's a lot of numerical evidence, for instance, in that case. So I think that's a situation where we're very confident about it. I mean, I think anything that's kind of within sniffing distance of non-abelian Hodge theory, I think basically everyone believes all those kinds of extensions of the conjecture, even though whether or not we're close to proving it or not. It's more the situation where you leave that world where I think maybe opinion is less clear.
Okay, I see. Thank you.
Thank you.
More questions?
Oh, yeah, Mark.
Wait.
Oh, thank you. Thank you. Oh, okay. Seems like going from GLN to SLN would not be much of a stretch. What's the problem?
It's so annoying. Yeah, so the idea is that one of the things that we use in this argument, which I did not talk about, is that we know we have a lot of information just about the cohomology ring on either side. I mean, they have the same cohomology ring. And we know, for instance, how they're generated. So in the case of GLN, the moduli space of Higgs bundles is generated by just tautological classes. So things you get from the universal Chern class of the universal bundle, you take like Kunitz components. And we know that those classes don't generate the SL moduli space because they lie, I mean, there's some finite group action, they all lie inside of the invariant part. And so what we need is we just need some way of accessing the other parts of the cohomology that you can't see in a way that makes sense on both sides of the correspondence.
But you know how to compute it, you just don't know how to relate it on both sides.
Yeah, that's right. So on the Higgs moduli space side, the other pieces of the cohomology can be understood using what's called endoscopic correspondences, so using some lower rank moduli spaces of Higgs bundles. But it's not known that approach, it's not known, I just don't know how to do that on the other side in a way that's compatible.
So on the wave side, the wave filtration canonical split. Can you see that from the perverse side? Is there Is that corresponding to something?
So, yeah, that's a good question. So the question was about, there's a canonical splitting on the weight filtration side. So on the Higgs moduli space side, I mean, there are, in general, if I give you a proper map, this sounds dumb. There are four, if I pick an ample line bundle, there are 4 canonical splittings, which seems to be the same as saying there are no canonical splittings. But nevertheless, there are kind of 4 a priori different ways of canonically splitting the preferred filtration once I make the choice of a relatively ample bundle. And so I think, do I know that? I don't think I know this, but the expectation is that in this case, those 4 choices all agree and then should agree on the other side. But I don't know of a direct way of seeing any of those statements. For instance, you know, that grading on the weight filtration side, it's a splitting that's compatible with the cup product. So the analogous statement on the left-hand side, I do not know how to prove. Is that true? Not without kind of going to the other side. I don't know how to see that directly.
More questions? So one quick question. Can you say again, so in this local curve Calabi-Yau threefold, what kind of sheets you're counting compactly supported sheets? Like curves set theoretically supported on a curve?
Yeah, that's right. I mean, there are, I mean,
and what?
So I'm doing like, you know, if let's say I'm doing on like the DT side or whatever. So I'm counting, you know, sub schemes that are kind of are proper inside of this non-compact Calabi-Yau threefold. And let's say if I'm doing on the DT side, I can just think of them taking like some weighted Euler characteristic of that moduli space. And so then the conjecture is that that generating function, whichever one you want to pick, can be read off from, in general, you take the moduli space of like one-dimensional sheaves on the Calabi-Yau threefold, and then kind of study the, you know, Hilbert-Chow morphism and play around with that.
I see.
And so, I mean, you weren't able to go to Yokonobu's talk because you were here, but that was that's some 2-cent summary of the conjecture in Yokonobu's case. And then in the specific case of that specific Calabi-Yau threefold that I wrote down, if you unwind both sides on the kind of DT side, that's just a calculation that, you know, was done from the old days, and you get an answer. On the other hand, you can do the answer with the perverse filtration, turn it into the weight filtration, and then you get this point count that was done also, you know, 20 years ago, and they just match up.
Okay. More questions? Okay. If not, let's thank Davish again.
穹苍广而横千，物合多容，星云璀璨，黑洞冥冥。观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物之理，数为基础，几何为根，方程为本。数学家以思考重塑了人类对万物的认知，物理学家以智慧让我们掌握不可思议的能量，理论计算机与信息科学家以想象赋予机器逻辑推理的使命。一朝开获，时空时伟。基础科学托举无数希望，推动人类文明走向下一次质的飞跃。时代之交，风云际会，朔玉流金，聚会北京，怀柔燕栖，群贤毕至。为表彰基础科学领域的重大进展，为科学家重塑好奇与探索之精神，在邱成桐先生倡导下，秉承开放与合作的精神，国际基础科学大会应运而生。大会聚焦数学、物理、信息科学和工程3大基础科学领域，邀请全球顶尖科学家研讨世界学问之大流， 追寻前沿科技之深邃，跨越国界与文化的差异，搭建国际学术交流平台，探索基础科学发展之未来。大会颁发基础科学终身成就奖和前沿科学奖。世界多国院士及诺贝尔、菲尔兹奖等奖项得主组成评审团。邱成桐先生担任终评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some award for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great